Okay, we are ready.
Ready to go? Okay. So, good evening, everyone. It's another one of our colloquia in-person series of the Department of the National University of Athens. Today, we're very pleased to have Andreas Eckart with us in person. It's a very nice thing since we are kind of at the borders of Europe, so we rarely have people here, so it's an honor for you to be here with us today. So Andreas is a professor at the University of Cologne, and he is a member of the Max Planck Society. He has been managing director of the Physikalisches Institute in Cologne until recently. He got his PhD in '83 from MPIfR for radio astronomy on the detection of extragalactic radio sources, but what he's most famous for, what he's been working throughout the years, is the Galactic Center, for which he's going to speak to us today. So then he moved to University of Arizona, then back to Germany at the Max Planck Institute for Terrestrial Physics, and then to Cologne, where he has been since then, right? 99. He has received several prizes in his life, including some team prizes, let's say, for his contribution to the Event Horizon Telescope, the Breakthrough Prize in Physics, but also some personal ones, including the Andreas Eckart Medal from Sweden, and the Ernst Mach by the Czech Academy of Sciences for his lifelong work on the Galactic Center, right? So this is what we're going to hear about today. And again, we're very happy to have you. Yes, thank you.
Yes, thank you very much also for having me. It's a pleasure to be here and to give a contribution and to meet people. Yeah, so what I wanted to do is, as I said here, give an update on some research aspects on the Galactic Center. But at the same time, I will also give sort of a small introduction what the Galactic Center is and why it is important and so on. So there are many aspects to it, and I will touch on some of them. And maybe if there are problems or questions, we can talk about it afterwards. So first of all, the Milky Way, as we can see it from the northern region, is a structure that is, of course, very important. It's a very large structure, and the center of the Milky Way is sort of in the south. Therefore, you cannot easily observe it from the north. And therefore, most of the observations that I will be talking about have been done in Chile, in the south, where the Galactic Center actually rises and gets to high elevations, so that can measure it very nicely. And the problem is depicted here. I mean, we are approximately here in the disk, in the galactic, in the Milky Way disk. And if you want to look towards the center, then we have to look through the entire disk. And in that disk, of course, there are clouds, dust, gas, and they absorb the light. So you cannot see the Galactic Center in the visual, but you have to go to other wavelength domains. For instance, X-ray domain is possible, radio, and also in the infrared or near infrared. So in the near infrared, the extinction is only 3 magnitudes, right? Whereas in the optical, it's like 30 magnitudes. So no chance. Distance, as we will see how that actually came about, distance to the Galactic Center is pretty much exactly 8 kiloparsecs, and it corresponds to 26,000 light years or so. So an important research field is measuring the stars, the stellar positions, and the proper motions of stars, measuring orbits. A lot of stuff has been done in that field. Here only a small summary. On the left-hand side, you can see a false color image of the Galactic Center that is composed by 3 or so band filters in the infrared, including also the L band, where you can see the dust. So you see some structures here. This is the mini spiral, the so-called mini spiral. That is gas and dust that is sort of orbiting the Galactic Center at some point. And you see some bright stars clustering at the center. These are mostly helium-rich giant stars, like 20 solar masses and surface temperatures of about 30,000 Kelvin or so, including some late-type stars in the perimeter here. And a very important late-type star here is Iris 7, because for technical purposes, that can be used as a reference star to fix your position, to do imaging, and so on and so forth. Then at the very center, if you zoom in here, and that is done here artificially, one sees a bunch of stars, which are the so-called S stars, S-cluster stars. So the S-cluster is the group of stars that is in the immediate vicinity of the supermassive black hole and that have high velocities, several thousand kilometers per second in their periods. And lots of work on these stars. It's about 100 or so of these S stars has been done, and including the first proper motion measurements, and now till orbits researchers gone. So this is what I'm going to carry you through on the Galactic Center. We talk a little bit about the instrumentation that has been used. Then we talk about some specific aspects that are interesting because it's a supermassive black hole and there is coming gravitational effects into play, like the periostron shift due to the space-time influence of the supermassive black hole, and also the redshift of the star S2. So that's the gravitational redshift is meant here. And then I will also highlight some of the recent S-star cluster research. So we are finding more and more fainter stars that are orbiting at a high rate and that get very close to the supermassive black hole. And the closest orbital timescale we have by now is like 4 years. So in 4 years' time, one orbit is completed. For S2, that's the most famous star, the orbital timescale is about 15 years. So it takes 15 years, and we have observed about 2 roundabouts of S2 about Sagittarius A star, about the supermassive black hole. And then also I'm going to talk a little bit on the bulk motion of plasma that orbits Sagittarius A star. I will come to the name in a second. And that is then bringing us very close, a few Schwarzschild radii only away from the supermassive black hole. And we will talk then also about the relativistic electrons that are radiating there and via what mechanism they will be radiating. Now this acronym here, Sagittarius A star, stems from the fact that in the early days, at least, the radio astronomers gave names to the sources according to the stellar constellations the radio sources were found in, and this source, and then they numbered them A, B, C, D. So this is the brightest radio source in Sagittarius, in this constellation Sagittarius, and it is an extended radio source, and it has also a compact component to it, and that is Sagittarius A star. And that can be identified with radiation coming from the supermassive black hole. So if I say Sagittarius A star, I always mean the black hole. Instrumentation. As I mentioned, we need to go to Chile to actually observe the Galactic Center well, because there it is actually culminating or coming very close to culmination. So it's then almost close to the zenith. And that makes things easy for astronomy. And the telescope that has been used most now recently is the UT4, Unit Telescope 4, because there all the high angle resolution adaptive optics instrumentation was mounted. So that has been used. And here you can see the 4 unit telescopes, Paranal, and the interferometry telescopes here, and a survey telescope over here. And the observing room is actually in this building here. And this year, these are ducts and canals through which the light from the different telescopes can be funneled if you want to do interferometry. Then an important instrument that recently has been used to measure properties of Sagittarius A star, both for the stars and the gas clouds orbiting it in its immediate vicinity, is the gravity instrument. And the gravity instrument is actually a VLTI, that is Very Large Telescope Interferometry backend. And that has been built by a consortium of which we are also part of. And the principal investigator of it is Frank Eisenhower at the MPI in Garching. In the X-ray domain, data has been used from both Chandra and from XMM Newton. They both have been observing the Galactic Center, and that's interesting for light curves, for instance. And we'll come to light curves then towards the end of the talk. Then the highlight to actually prove that Sagittarius A star is a supermassive black hole is to pinpoint predicted or expected gravitational effects like the periostron shift and the gravitational redshift. And that has become possible, also now including the gravity instrument. And that is an additional indication for it being a supermassive black hole. The other indication, of course, is measuring the mass of it. And it has 4 million solar masses. And that measurement is a very solid one, as we will see. So what happens if there's a star orbiting a very heavy mass? And there is basically 3 effects. There's one effect that is the relativistic periastron shift. Due to the fact that this mass influences space-time, there's no elliptical fixed orbit, but the orbital time scales at the periastron and the upper astron are different, and therefore you start having a Rosetta shape structure of the orbit. So that is prograde. In addition, if you dive into a mass, into clusters, into a stellar cluster, then the mass underneath the star changes. And that leads to another periastron shift, that's a possible periastron shift, that's the Keplerian Newtonian periastron shift, which is actually a retrograde. So you have to make sure that you don't mix up these 2 things. But it turns out that the mass that is actually being resolved by the S-cluster stars is minimum compared to the 4 million solar masses. So we probably don't see a strong effect of this phenomenon. And in addition, what you also have to worry about, that has also not yet surfaced, is that if there are other heavy masses like 10⁻³ solar mass, intermediate mass black holes, for instance, or several 10 solar mass, 20 solar mass relicts of massive stars, then that leads to a certain granularity of the underlying gravitational potential. And then that can also lead to changes in the orbit. But right now, the only thing that has been observed positively is the prograde relativistic periastron shift. And the way we have done this in the beginning is by looking at the orbital data of stars like S2. And if you are on such a dashed Rosetta-shaped orbit, then if you do fits to the orbital parameters and use only the upper or the lower part of the orbit, you get different solutions. That then leads to different orbital elements, and these changes can be used to characterize the relativistic character of the orbit. That means delta omega, so the way how the orbit lies in space, that changes depending on where you fit, and also to a lesser extent the ellipticity and the long axis, they also change if you compare fits to the lower and upper part of the orbit. And from this, we were able to actually say that the amount of periastron shift that is in the data is of the order of 0.0008 in this relativistic parameter, which is the relation between the Schwarzschild radius and the periastron distance. And the expected value would be 0.777 approximately. So it comes very close to it. Also, the amount of shift that we have detected with this method is of the order of 14 ±3 arc minutes per revolution. And the expected value is 11. So also, again, rather close. And that then led to an ESO press announcement showing that this effect is probably present in S2. And it will have the effect that the orbit doesn't fall back into its elliptical orbit, but it's a little bit displaced, as you can see here indicated. Of course, if you have higher angular resolution, you can do better than that. And that was now done with the gravity interferometer. And for this interferometer, Cologne built the 2 light combining spectrometers. So they are in the heart of that instrument. And that's a system, optical system here consisting of lenses and prisms and so on. And there the light then gets focused on little fiber stacks, and the fiber stacks then combine the telescope light in an appropriate way. And in order to do interferometry, you need more than 2 telescopes, of course. In the radio, that can be done relatively easy because you have the electrical signal on a cable. So you can have longer or shorter cables, or can influence the traveling time along the cable. So that means you can compensate for the differential time the wavefront needs after it hit one telescope to hit the next telescope. So by compensating that, you basically shift the telescopes into one plane perpendicular to the incoming radiation. and then can use these telescopes as double slits, multiple double slits. And there's also a velocity problem involved here, which I'm not going to talk about. In the optical, it's more difficult because you cannot easily, without penalty, put your optical light onto a cable, where you can use fibers to a certain extent, but that brings other problems with it. So the cleanest way of doing this path length compensation is actually to do it physically by mirrors that move. And those moving mirrors are here in these light ducts. And here you can see people in this light duct. And here you see the slides along which a card is moving that has a reflective mirror. And by moving this card corresponding to the change in position of the source in the sky, you can correct for the differential delay of the wavefront as received by 1 or 2 telescopes. This sounds easy, but of course, as you can imagine, you need to control the movement of this mirror to a fraction of the wavelength. And you cannot simply do this by putting a car on a rail. So that is done in several linked steps. So yes, the car is on the rail and it travels with the required speed along the rails. But the reflective mirror is put on a voice coil so that the mirror can be moved quickly and precisely in addition to that. And on top of that, the reflective mirror is also on a stack of piezo crystals, so that you have 3 stages of compensation: the physical track, then the voice coil, and the piezo stack. And these all have overlapping sensitivity sections. And with that, you can then finally control the path length to within better than a fraction of the wavelength. And then that leads to fringes. And that is an image of the gravity instrument. Here you can see the big viewer, here a person working behind this. And here you see the first fringes as they were obtained by combining 2 telescopes with this gravity instrument. The big advantage of the gravity instrument, because other interferometric instruments had been there in place, also in the infrared, but the big advantage of this gravity instrument is that it has basically 2 channels. So you can observe a reference star plus your science object, and they can be separated by a few arcseconds. So this way, we could lock on a star in the galactic center cluster and at the same time look at other stars or the very center itself and use that tracking information from the offset star. And this way you can be very sensitive and very precise over short distances in space, in angular distance in the sky. And in fact, this periastral measurement has been performed. And here is the indication of it. So again, one needs to hold grip to a section of the orbit in which the effect is not strong. That is when the source on its descending part or ascending part, and if it comes close to periapse and swings by, then the biggest changes in omega occur. And you can see these deviations here as measured with the gravity instrument. And the result is, again, that we have 4 million solar masses, and the expected effect is well described by relativistic effects. Another thing, in addition to the periastron shift, is the gravitational redshift. That is, if the star comes close to the central mass that it is orbiting, then the wavelength of the emitted photons is effective, and the source appears redder to us. And this is a combined effect. We are interested in the gravitational redshift effect, but there's 2 effects that actually come in place when you discuss the redshift, Z as delta lambda over lambda. You can do this expansion, and in the beta is V over C, the velocity of divided by the velocity of light. And this B squared term, this B2 comes actually in 2 sections, B2G and B2D, and that is you have the transverse relativistic Doppler effect. So that is the Doppler effect that occurs always, also not only if the source is moving back and forth along the line of sight, but also if it moves perpendicular to it. So that is an effect that comes into play when you do relativistics. But also you have the gravitational redshift effect. So those 2 effects cannot be separated. They have to be treated simultaneously, and they're of equal importance. So they both come in with a weighting factor of 1/2. But it can be done. So if you think about how big that could be, that effect, it comes out to be about 10⁻³ for Z, for the redshift. And that comes out to be about 150 or 200 kilometers per second. So that can easily, as predicted here, be observed with spectrometers. So this is the amount of redshift imposed to the light of the star that you expect from the gravitational redshift effect. And in fact, it has been measured by the two major groups, that is the gravity collaboration that we also belong to, and by the UCLA people that use the Keck telescopes, the two Keck telescopes. And as you can see here, this red line here is not a fit to the data, but it is the predicted way the data should look like. And as you can see here, we have published earlier, so just after the peak, and when the star was descending here, the redshift effect became minimal again. The publication went out, whereas UCLA people waited a little bit longer to be absolutely sure that you also measure the other side of that graph. So that could be done. Now, apparently, for these relativistic tests, the S stars are of certain importance because they come very close to Sagittarius A star, and there these effects manifest themselves even further. And we keep finding more reference stars, more S stars, and you have to do that. There's some publications on this, and this is a recent summary of the S stars that we found. And you have to do that by looking repeatedly at high-resolution images over the years. And this is a little collection of post-stamps maps, basically, each about an arcsecond in size. But here you can see what the problem is. It's a very messy region, right? Because there are so many stars. And this is only a sample of images given here. And you do see that the star is in here, right? You do see it, but you have to keep track of these images from year to year and compare the images to see how things are moving there. And once you do that and track it down, then you can come up with orbital tracks. And then another thing we did, since we now went into the heart of the S cluster, and since we found very, very fast moving stars, and since we wanted to highlight that these stars have been found in Cologne, we started to call the sources after the famous Cologne perfume. You know this 4711. So the first of those stars that we found, we called S4711. And then we kept counting S47, 12, 13, and so on. So in any case, that worked quite well for us. And here you can see one of the stars, how it looks like if you actually do the orbital track. So this is how it looks on the sky, not very attractive, but this is how, if you resolve the data points and plot them separately in declination and right ascension. So that is then the orbital track that the star fulfills while it's flying on its orbit around the central mass. And here's a few more. This is 47, 12, 13, 47, 14, 15, and then comes another interesting object that is then 47, 16, I think, where we have both Keck data and 12 epochs of imaging data and also interferometry data. And that is now the star with, to my knowledge, the best coverage over as a function of time. You can see we have tracked it down for several periods. It has an orbit time scale of only 4 years. And the closest by data, that very close to the periods, they have been obtained interferometrically. And this is an indication of its flux. So we keep on measuring the same star, so we don't hop to different stars. This is an indication of velocity, line of sight velocity. So at 2 positions, we have spectra where the star was discernible against the background. and this is the helium-1 line and the bracket gamma line of the star. And by this you can monitor here one position very close and one position further away. You can see that the star is not only moving in the plane of the sky, but also has a background back-4 motion due to the inclination of its orbit. And this is the measurements distributed over the orbit. And as you can see here, we are now really far in, right? This is arcseconds on the axis. So this is only 80 milliarcseconds in size. So very, very far in. And these red points are interferometrically measured by gravity. And all the other points with larger uncertainty bars are measured from imaging data. And here's a corner plot so that you get also the distance and the mass simultaneously from these measurements, because this is what happens if you fit an orbit. You have to fit simultaneously to the mass and the distance, and that comes out to be very well. And here again, important data that characterize both the orbit and the relativistic character of the orbit. So the relativistic periastron shift can be determined, and also the expected Doppler shift yet to be measured can be determined. This is now the overview over the inner S star cluster. So far, you can see it becomes really very, very crowded. And you can also see some of the sources like S62. Oh. Yeah. Now it should be fine again. Can you see it? Okay, so yeah, so this is now an overview of the inner S clusters. You can see it's getting really crowded here, and some of the stars like S62 or S4612, for instance, come very, very, very close to so only a few 10 short-circuit radii to Sagittarius. Now, this is a list. You don't have to read this, but just to tell you that it's there. This is of the orbital parameters and also the estimated relativistic effects that we can observe in the future by tracking these stars precisely. Now, these are the stars. They bring you in a couple of 10 milliarcseconds or so close to the supermassive black hole. But if you want to get closer even, you have to use different methods. And one method is over light curves, and another method would be direct measurements with the interferometer. And what you would expect then is that if you have a plasma blob, which is emitting radiation, continuum radiation, it will change its brightness depending on how it is traveling relative to the observer. So if it comes close to the observer due to relativistic bulk motion effects, due to aberration, it will become brighter. And if it moves away from you, it will become fainter. And there's also other effects involved here. So this is the effect that is expected, and that is what we can also model together with the colleagues in Prague. We have developed a relativistic trace model that can also fit near-infrared data. And the effects that you can then get out of these models are shown here. So here you have the observer. That is in the field of view, and here's the supermassive black hole. And if you have an orbit, if you have a star or a plasma cloud orbiting the supermassive black hole, there's a few interesting points. One is if the point is directly behind the supermassive black hole, then you get a lensing effect because the light is diverted by the gravitational field of the supermassive black hole. So you expect a lens effect, i.e. a magnification of the light intensity. And if it sort of moves around the corner and the light is also deflected by the gravitational field, there will be a point where the motion towards the observer is largest, and then you get a boosting effect. So it becomes also brighter. So this is how it looks like for the light curve for a cloud orbiting the supermassive black hole and having different distances and inclinations and sizes. Yeah, so then the light curve changes correspondingly. But it has one common feature. There's always a lensing shoulder here, also in these less interesting cases, lensing shoulder here that comes due to the lensing effect. And then the big boost is due to the boosting effect. So there's two peaks that you can expect, or you always have a shoulder here in that peak. Actually, if you take the brightest X-ray flares, that can actually be observed. So there's always an indication of a shoulder on the right side of the flare. And here also in this interesting flare by Ponti, you actually see a very pronounced lensing peak, followed by the Doppler boosting peak. And this is now interesting. You can use these light curves and make a fit using this relativistic program that I've presented here. And you can do that fit just to the shape of the light curve, not involving any estimate of mass, yeah, just the shape. But then as soon as you introduce the time, yeah, if you tell the program so and so many steps in your time unit correspond to so and so kiloseconds, then you also pinpoint the mass. So by making these scaleless fits of the flares for this relativistic shape and introducing the time, you also introduce a mass automatically. And that works quite nicely. So you can derive the mass of Sagittarius A star just from the X-ray light curves with this model constraints. And you get, for these different flares, you get values of the order of 3 to 4 million solar masses. So that works very nicely. And we could also apply this method to one other source, extraterrestrial supermassive black hole, where we can rightly assume that the variation is due to motion of plasma clouds, rather than due to variations in the accretion. Now, of course, that was an indirect measurement because it's light curves, and you fit a profile under the assumption that is manifested in the relativistic program, and then you deduce information on the system. But it would be nice to actually see such a cloud moving. That is very difficult because the cloud motion will be on the sky will be of the order of a few 10 micro arcseconds, and you don't have the angular resolution to do that. But you have angular resolution at the VLT of the order of a milliarcsecond, a few milliarcseconds. But that's not enough to do that measurement. However, since you can measure offset distances very precisely with that instrument, if that source is moving, you can check the motion, so that is the centroid of the emission during a flare by a few 10 microarcseconds. So there you have the exactness. And that actually has been done. So there's at least one or two events where actually the centroid position followed an orbital shape on the sky during a flare. So this is the flare. The red and blue dots are the right ascension declination measurements of that orbit. And here you see the orbits on the sky. And that's the position of the supermassive black hole. So in other words, the centroid motion does reflect the orbital motion of a gas cloud in orbit about the supermassive black hole. And it does so in full predictive power to what is expected. And another important measurement, of course, of that general region is to see the gas radiating as it is in the vicinity of Sagittarius A star. And for this, the radio interferometry comes in. So the Event Horizon Telescope has the resolving power, as you can see, by several 10 micro arcseconds. So they can actually make images of that region. That has been done for the two biggest black holes in the sky, so to speak. That is Sagittarius A star with 4 million solar masses, because it is so close. And it is in N87. It's much further away, but also several orders of magnitude more massive. That's why they come out to be almost the same size in the sky, but they come out to be the two largest supermassive black holes. For M87, since it is much larger, the variability is not that strong, and the image signature of plasma orbiting the supermassive black hole comes out much nicer, because there's one part is bright and the other part is dim. And as you remember, material that is moving towards you gets Doppler boosted, and material that is moving away from you gets deboosted. So here we are looking at the boosted side, and here we're looking at the deboosted side. The problem with Sagittarius A star is that the image that could now be produced is not that telling. And so it not clearly shows the relativistic effect that you would expect for plasma clouds in the vicinity of Sagittarius A star, because it has 3 peaks. But that comes due to the fact that the variability of Sagittarius A star is much higher. Now, if you want to do an interferometric image, you need to fill up the UV plane, so you need to observe it for at least 8 to 12 hours, and then you can invert the data and produce an image. But during that time, Sagittarius A star is variable, and you cannot easily decouple the variation due to its intrinsic variability from the variation in the interferometric signal that you expect by resolving its structure. So that's why it was very difficult to do this. And many imaging attempts with different programs by different groups have been combined to get this final image. Now, relativistic electrons and the radiation that comes from Sagittarius A star. I've mentioned several times plasma clouds that are radiating. And the question is, what is the radiation mechanism? How are the particles accelerated? And how are the variations at different wavelengths connected to each other? Because Sag A star is a variable source in the radio domain, in the near-infrared domain, and also in the X-ray domain. This is 101 information on synchrotron radiation. So what we have is in a trivial setup, what we have is a spectrum of relativistic electrons that have energies from little gamma 1 to little gamma 2. And the slope is P equals 1 plus 2 alpha. That comes in through theory. And if you transform this spectrum of relativistic electrons now into a spectrum of photons that they emit, you also have a nu 1 and a nu 2 that are coupled to the minimum and maximum energy of the electrons. But then you also have a spectral index alpha, which is here embedded in this spectral index P. But you have a different problem that now the longest wavelengths cannot leave the plasma in which they are being produced. Here you have optical depth effects. And here the optical depth is actually not 0, but unity at that point. And so the lower part is more difficult to be seen. But in the optical thin part, you have a spectral index of alpha. And then the radiation is connected given by the synchrotron process, is linked to anything that is the magnetic field, the source size, the turnover frequency nu m, where the optical depth effect sets in, and the flux density at that position. They're all coupled together. And moreover, they're also subject to relativistic effects. So there's the relativistic boosting factor due to the entire motion of the cloud, and there's also effects of relativistic electrons as they fly with high speed in magnetic fields. And another thing needs to be considered. If you produce synchrotron radiation, that is, you have relativistic electrons embedded and flying in a magnetic field, then they undergo also scattering events. That is, the sub-millimeter photons that are being produced by synchrotron radiation scatter off from exactly those electrons that produce them. And then you have the inverse Compton effect. The classical Compton effect that you sort of learn at school is that, that an electron absorbs energy from the photon, and therefore the photon becomes redder. But if you have relativistic electrons, it actually goes inversely. That is, if the photon is scattered from a highly relativistic electron, it gains energy and is being scattered from the submillimeter into the X-ray domain. So that is the synchrotron self-Compton effect, or inverse Compton effect. Various ways to do that. And you need about a little gamma of the electrons, that is basically the speed or energy of the electrons, of 10 to the 3, which can easily be produced by acceleration mechanisms. And then you can actually produce a large section of the X-ray spectrum by simply scattering the optically thin radio spectrum into the X-ray domain. And there's another interesting fact comes in here, because you can now look at the spectrum of flare fluxes that are being produced by variability effects. And though this distribution has a certain shape, which is given here. So this is basically count rates, and this is the flare flux given here, the count rate, and this is the probability with which you observe flares. And in order to reproduce this shape here, you basically have to assume how the flare intensity is coupled and what spectral index is there in the flare intensity. And there is two ways to do this. You can have a power law, and then you can have a hard cutoff of the power law. And then you can, by modeling, look what kind of a distribution you would expect and how well that fits the data. That has been done, and it has led to a power law exponent of about 2, with quite a good precision. But another way to model this is saying there is no such thing as a hard cutoff in nature. All the cutoffs, even if they're hard, are more or less exponential. So you have an exponential cutoff, and for this you then find a spectral index, or an index of that distribution, of 1.66. And why is this interesting? This is interesting because if you go in with synchrotron self-Compton formalisms, then you see that this spectral index is coupled to the intrinsic spectrum of the flare flux, and that you expect this coupling to produce an alpha, so a spectral and a power law index of 1.6 from theory. So this 1.6 you get by having the X-ray and the infrared being coupled through the synchrotron self-Compton effect. So this is a semi-analytic approach here, and that gives you the 1.6. And if we fit the data with a function that I just described, namely an exponential cutoff, power law of the exponential cutoff, then that power law comes out to be 1.6, very close to the value expected from theory. So if you want, this is an indirect proof that the radiation being produced by the plasma clouds around Sagittarius A star are very consistent with the synchrotron self-Compton mechanism. And that is, that is easy to have. As I said, this gamma of 1,000 or so you get through acceleration mechanisms, and the densities that you then need to have for this gas to be synchrotron self-Compton is of the order of 10 to the 6 to 10 to the 7 per cubic centimeters. It's not too high compared to other effects. So that is a good scenario, so to speak. So in other words, what you have is most likely that the radio to millimeter spectrum of Sagittarius A star is actually scattered into the X-ray domain, rather than being only linked by direct synchrotron radiation between the two domains. So scattering is most likely essential here. I was advertising this paper by Witzel 2001 earlier. That is now a theoretical approach to the variability data that serves all the statistical requirements. So it starts off with random numbers. It sets up certain power law distribution for the flares, and it produces, by introducing all sensible effects like optical depth and adiabatic expansion and so on, produces then also sub-millimeter light curves and near-infrared light curves and X-ray light curves that have the same statistical distributions as you measure them. So this is the most conclusive, inclusive program or modeling approach that is now taking care of all the effects that we know. And in that model, you get exactly this shape of the spectrum. So you have a radio spectrum peaking in the sub-millimeter domain. Also, the relativistic gas expands, and therefore this peak shifts in frequency that is described. And you have then a synchronous self-Compton scattered part, which can account for the X-ray flare flux, and also can account for the overall spectrum that has been observed. So, and that allows us to describe now these plasma blobs as plasma blobs that emit while they are being produced, and both relativistic expansion and relativistic contraction may play here a role, and that then produces these characteristic flare signatures observed in the infrared and in the X-ray domain. Now, finally, we can make use of these flares, and by modeling them and seeing how fast they move about Sagittarius A star, we can also use these flare blobs, these flare events, to determine the mass of Sagittarius A star. And that mass, again, is consistent with 4 million solar masses. So now we have the mass measurement. So here you are in the stellar cluster. You start resolving the cluster until you hit a region that is dominated by the mass of Sagittarius A star. Here you have the most famous, somewhat outlying S2 star, and here you have other stars, S-cluster stars. Here you now have the gravity flares, and this is the radio size as obtained by the EHT, and this is where the event horizon supposedly lies. So we can now measure all the way from arcseconds down to a few 10 micro arcseconds and determine the mass, and also have information about the size and motion of gas in the vicinity of the supermassive black hole. And that allows you to span these areas here that are outlined by these red dots. This is basically a similar graph as the one before, but only more quote-unquote physical. So this is a measure of the potential. This is a mass measure of the supermassive black hole. And you can see that the precision of Mercury, that allows you to see the influence of the one solar mass object, namely the sun. The Hals-Taylor pulsars, they are very massive and very nearby pulsar binaries. They allow you to measure relativistic effects. And now we have the stars as they have been observed here with gravity, for instance, and we have the X-ray hotspots as I outlined from the light curves. And here we now have the gravity instrument measuring also the spots actually moving. So you see, we get very, very close to the totally black hole dominated region. So we can map out these effects very nicely. Yeah, so basically we can probe the relativistic environment of Sagittarius A star in great detail, now using both the stars and the plasma blobs. And that will hopefully continue. So in Cologne, we have been participating both in building the James Webb Telescope, the MIRI instrument. So we have been building parts of the MIRI instrument. And also we are building part of the mid-infrared camera that will be installed at the 40-meter telescope by ESO. So, and of course, the Galactic Center will be a prime target of those instruments, and we are about to get some data. In fact, some data has already arrived, not yet by MIRI, but by a near-infrared instrument on board of James Webb. So they have been observing 4 fields in the vicinity of Sagittarius A star, just for test purposes, to investigate the stellar content, basically, and the spectra of all stars contained in these fields could be produced. Here we see a combined spectrum, so you can see very nicely the Paschen line, the bracket beta line, bracket gamma. You see CO absorptions from the underlying stellar cluster with late type stars and several other lines. So that allows you to make a direct census of the types of stars in the underlying cluster using James Webb. But in upcoming sessions, like in a few months or so, we hope that we get then a measurement of the central arcsecond that includes the S-cluster stars and Sagittarius A star. And that will be then very interesting what that could show. And that is the end of this summary of most recent Sagittarius A star measurements and data that is around and what kind of science is being done right now. Thank you very much.
Maybe we would just first the online participants if they have any questions.
Yes, are there? Just a second.
There is one hand raised by
Yes, yes.
Hello, Professor Eckart. Thank
Hi.
you very much for this great talk. It's really amazing what, how accurate measurements you can do with this wonderful instrument with gravity, I guess. The first thing I would like to ask is, in the first part of your talk, you showed theoretical curves about the S stars. And you have created them with all the observational points that you get from these stars. Do you believe that the interaction between these S stars are measurable? Like what Saturn and Zeus are producing on Mercury, for example?
I don't think so. I don't think that the interaction of the stars amongst each other, like one S star to the other S star, that is a very strong signature that can be observed with the precision of the instruments that we have right now. What we right now see is the influence of the supermassive black hole, 4 million solar masses, on these supposedly 1 to 10 solar mass stars. Right? That is what we can observe. So that's the relativistic periastron shift. That is the gravitational redshift. And even the lens steering effect is very, very difficult to be observed because then you need to go with high precision measurements to a source that is moving very close in. So I doubt that that will be easily possible. So I think we are here at the limit of what we can do, but what we can improve on is getting more stars for which we can determine these relativistic effects to be absolutely certain how space-time is configured in that region.
Okay, I understand. Thank you.
Welcome.
I don't see any other hand raised.
at that point, where you see all the contributions in the masses of the star's orbit, there was a granularity to the extended mass. What could this be? How is this observed? What makes us conclude that there is some kind of extended mass that why can it be more point masses or influences of smaller point masses that are
so there's two ways to approach this. One is the exactness with which you can determine the central mass, that is 4 million plus minus some uncertainty, and the extended mass can be within that uncertainty. And it is now estimated that this is of the order of 10 to the 3 or 10 to the 4 solar masses. So that is the uncertainty. So that is your volume with which within which you can sort of speculate about an extended cluster. The other track that you can follow is the Galactic Center Stellar Cluster is basically a gigantic graveyard, because many stars have been produced in the vicinity and have died at some point, supernova explosion, etc. pp. And you also have most likely a large amount of pulsars there, or neutron stars at least, which are not very luminous. So it's easy to put in a stellar mass that can not be observed directly or easily. But we have not yet seen any influence of those stars on the orbits of the S-cluster stars. So for this, it is also important that one keeps tracking the S-cluster orbital elements, because if this granularity is of any interest and influence, then that may be reflected in the precision or in the magnitudes to within which you can determine the relativistic periastron shift, for instance. But yet not possible.
So there's just a limit on how much this can contribute.
Yes.
And an estimation of the maximum of that mass, the maximum of that possible mass, would have not said something like that, the contribution.
No, that is, as I mentioned, that is contained in the uncertainty with which you can measure the 4 million, right? And if you make use of that, then the upper amount of mass can only be of the order of 10 to the 4 or slightly less than that.
A couple of encyclopedic questions.
Yes.
Not so direct, perhaps. The one is that there is this cloud orbiting on much longer time scales. I think in the optical and infrared that you see by the starting years. Isn't that a much longer orbiting cloud?
This is the cloud, yes.
Is this possibly connected to the X-ray beam? Could there be like some gas that flows instead of a crate?
Yeah, I have to disappoint you. We get different results here. This gas cloud, that was supposedly a pure gas cloud that would then be go through periapse and be disrupted or be accreted partially. That doesn't exist. There is an object, there is infrared emission of an object that is traveling on that path, but it contains a star. So it's a star with an infrared excess, basically. It could be a very young star, with a small amount of luminous material. It could also be a result of a binary merger. That would have similar specifics. And also, we cannot confirm the fact that the orbit of that star actually changed due to braking effects. That you might expect from such a gas cloud. It is on an elliptical orbit and it contains a star. And there are several papers on this that we have written. And it's a source of a family of sources that have infrared excess. And to our belief right now, these are traces of star formation. So these are younger stars. So it is possible to produce stars in that vicinity. Because there was always there's a standing problem. this dilemma that some of the stars look very, very young. Yeah, so you cannot produce them with a standard star formation process and then carry them in, because that would take too long. So you have to produce them in situ, so in the stellar cluster. That is possible. There's also papers on this. So by compressing gas clouds while they move in, and you can produce stellar mass spectra which are standard in their in their mass index. So that is possible. So star formation is possible in that region. Slightly different from what the star formation looks like outside such a region. And we think we see traces in that population of dusty stars.
So the second one is technical, but the part of the instrument that you build, I didn't understand so you said that you move the mirror in 3 ways, so that there is a subfield movement, so that you can record it.
Well, we don't do that. ESO does that, right? Our instrument is only a back end instrument.
Oh, okay.
It's a back-end instrument. There's some measurements also done on control lasers that also reach the gravity experiment, so that allow us to have exact control of the position of mirrors and so on. But the motion is actually done by the ESO environment, the VLTI environment.
So you mentioned 3 mechanisms.
Yes.
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 You mentioned the rays.
Yes.
You mentioned some piezo, this is changing
Yes.
shape, and the intermediate I didn't understand.
It's a magnetic tool, a voice coil. It's just a magnetic coil, so you can move that thing magnetically back and forth, and on top of it is the piezo stack. So you have three motions, and they all have control regions that overlap with each other, and that's why you can couple them together. So they all 3 move, yeah, and that motion is controlled and allows you to have the telescope connected with that precision that you need to see fringes.
I suppose that we call them voice coils because they are like speakers.
Yeah, yes,
because the coils of the speakers are called voice.
yes. And
are they actually refer speakers?
I don't know where they come from. But you can, but that effect of motion through voice coils you can easily measure at home by just touching your loudspeaker, right? And then you see how things move.
I have also a question which is rather naive, but I was wondering what are the masses of the S stars? Do you have estimates of their masses? And one more question, can you have an estimate or can you measure the mass loss rate of these young stars?
Yes. The brighter S stars, they have masses of the order of 15 solar masses. And you can tell that from their spectra and from line ratios and whatever. So they look like B stars. And so they're typical B star masses. Some of the fainter S cluster members, they may have like 2 solar masses, 3 solar masses or so. So that is also possible. And then, yes, from those stars, the S stars, they are not bright enough, not hot enough to have a significant mass loss. But the helium stars in the larger cluster, they are very bright, and they do have, they're also of the order of 20 solar masses. But there, in some of the lines, we see a P signal profile, and from the P signal profile, you can deduce the mass losses. And the one with the heaviest mass loss is Iris 13 East, and that has a mass loss of the order of up to 10 to the 3, a few times 10 to the 4 solar masses per year. So that means they're very young, and they will certainly not stay a long time in that with that behavior, because I mean, at some point you can't support mass loss that high for a very long time. But it just tells you that they're young.
One more question related to the zero transect quantum model that you mentioned to the end. So you said that you created a model by using the primary information of the near-infrared and X-ray light waves, and this was fed to the program and computed secret spectra. So did you also compare what are the predictions of the model in terms of light waves? So how these compare to the realistic light waves? And the second is, which parameter did you choose? Did you change in the model in order to produce this light wave? So was the magnetic field strength that was changing? Was it the luminosity in the realistic element that was changing?
It's some of they're all important, but the ones that you can vary are the size and the flux. Yeah, and then the rest is also, of course, an assumption. But these are some of the more important factors. So with the size, you control the self-common scattering. So you need a small size to do self-common scattering. For a large cloud, that doesn't work. But the sizes that are that are required here, they are fully consistent with the sizes that you need to do these other relativistic measurements, like blobs moving around Sagittarius A star, or actually the blobs that have been measured in an imaging way with gravity now. Their size is exactly of that size, namely 10 microarcseconds, that you need to do SSC scattering. Right? If you put in that size, then the SSC process comes into play.
So I also wanted to comment that this kind of approach is very common to people like us working on laser or AGN jet emission. So there was a paper that we actually followed a similar kind of thinking with a master student coming from the University of Athens, where we used gamma ray lighters and we inverse transform them in order to create time series for magnetic field strengths and size of the region and stuff, in order to produce a common model. So this is a very nice, like a common ground that we.
Yes. Yeah, the common ground is basically given by the fact that you have synchrotron radiation, right? And you have to play, and you can play with it. And the fact that it is synchrotron radiation is also clear because it's polarized and is fast in variability, and you see quasi-simultaneous variations in the near-infrared and the X-ray domain. And the synchrotron self-common mechanism is the only mechanism that allows you to do that. So it cannot be thermal or something like that, or Bremsstrahlung. So it needs to be emission from relativistic electrons.
There is one more question
Yes.
by Andreas Eckart.
Yes.
Yeah, hello. Thank you very much for your talk. I'm sorry I couldn't be there, but I'm in Heidelberg right now. But I have two questions. It was an excellent talk, but I wanted to ask you for the. You talked about mass loss. Can you estimate how much you can feed the black hole? What is the m dot one could give order of magnitude?
Yeah, that is a very good question, and there is no good answer to this. The amount of gas that is available due to mass loss, so we have about a dozen stars or so that show these P-signal profiles, and we know approximately their mass loss. So in principle, you have something like 10 to the -3, a few times 10 to the -4 solar masses per year available that could be accreted. However, if all of that material would be accreted, then the luminosity of Sagittarius A star would be about 10 million times bigger. Yeah, so it's clearly not accreted. So that's why, but on the other hand, you have this gravitational potential, right? So that's why the accretion rate that you need to consider changes as a function of radius. In other words, a small amount is being accreted, gives rise to the luminosity of Sagittarius A star, but at the same time also produces a wind coming from Sagittarius A star that blows away the incoming material. Yeah, so you can have a wind going out and material coming in at the same time. Yeah, that is possible. So actually only a minute fraction of the gas delivered by the stars in that region is being accreted. It's a very small amount. It's 10 to the minus 8, 9 or so solar masses, something like that. Of course,
yeah.
I mean, it depends on what you want to describe and what you put in as assumptions, right?
Yeah, thank you. Because that was my inquiry. In other words, if you feed so much matter, the black hole, this would shine quite a lot.
Yes, it doesn't reach it. It cannot reach it.
Yeah.
On the other hand, it's a very difficult observable, right? It's you can only indirectly measure the mass loss.
That's correct. Yes. And my second question has to do with the synchrotron SSE. It is well known that if you somehow increase the synchrotron radiation, SSE decreases non-linearly. So if you have a flare, for example, that you go up by factor of 2, in synchrotron you go by factor of 4 in SSE. Have you observed anything like that, or there it is very quiet? I mean, it is a very stable source.
Well, if you talk synchronous self-quantum purely, then depending on the characteristics of the cloud that is emitting, and depending on its motion, the radio infrared spectrum will be scattered as a whole into the X-ray domain. Yeah, but this is under pure conditions. Now, things become complicated if you introduce spectra which are not hard cut off and so on, if you have optical depth effects and so on. So then things become slightly more complicated. But all of this is included in this code by Witzel that includes all the effects that we have been measuring, namely the quasi-simultaneous character of the near-infrared and X-ray emission, and the optical depth effects that we think we see if we compare radio flares and infrared flares, because if they are coupled, then what is flaring first, basically, and at the same time as the infrared, is the high-frequency submillimeter, which you cannot easily observe. And then at lower submillimeter frequencies, that flare arrives later due to adiabatic expansion. So that's why there is, in some of the flares, if we use this interpretation, we do see a time lag of the order of 2 hours or something like that. So the radio is lacking 2 hours behind the variation in the infrared and in the X-ray domain. Of course, this is much more complicated because not all radio flares you need to be able to see in the infrared. Not all infrared flares you need to be able to see in the X-ray domain, because it depends critically on the characteristics of this plasma blob and on the magnitude of the flare that you observe. So, and then you also have the spectrum, right? So, and the source is variable. So you need to really put a lot of trust in the identification of flares at different wavelengths. This is what happens if you do a single flare analysis. Then you have that problem. But the strength of Witzel's program, for instance, which uses the data that we have been gathering over so many years now, is that it can reproduce the in-band characteristics of the statistics of flare fluxes. So it produces the right amount of variability in each of the wavelength domains, in the submillimeter, in the infrared, and in the X-ray domain. So there's two ways to model the flares: either on a single flare way, but then you have to put in some identification of the flares at different wavelengths, or statistically, by just looking at the statistics independently, the statistics of the flares in the radio, infrared, and X-ray domain.
Okay. Thank you very much for your talk and for your answers.
Another problem is it's difficult to observe these flares, right? Because the flare times are a few hours, and and you can only observe the source for a few hours per telescope from the ground. And a little bit better, the situation is using a space telescope, because then you can stare for a longer continuous time at the source, but that has also been done now.
Yeah, but statistically, you would be able to say something, because the amplitude should have been larger.
Yes.
Yeah. Or, of the SSE component, I mean. Yeah, thank you.
Depending on the efficiency of the scattering, and the efficiency of the scattering depends critically on the source size.
Okay. Thank you.
Yes, so I don't think that we have more questions. I mean, we can keep discussing, but thank you very much for this.
You're welcome.
And thank you for being here. And
Yes, it's a pleasure.
informing us about the Galactic Center.
It's a pleasure. Thank you.
Thank you very much.
Thank you.
Thank you all for joining.